Hello, let's talk about the laws of motion. So, first is Newton's first law of motion. Um, I'll read the statement and then explain it a little bit more. So, every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero force. So, let's think about this first with the idea that it's hard to start a heavy object moving, but it's also hard to stop it once it starts moving. Um, this relates to inertia. Inertia is also why the trick of pulling out a tablecloth from under like a dining set can work. Um, the dishes and things are not attached to the tablecloth, and the motion of the tablecloth is not enough to get them to want to move. So the tablecloth slips out from underneath them. Obviously, you have to be pretty good at cleanly pulling out a tablecloth to make that work. But an example you could try at home is with a coin on a cup and an index card or like a playing card. Set the card on top of the cup, put the coin on top of the card, and flick the card off of the cup or pull it off, whichever works. And the coin should, if all works according to plan, fall into the cup instead of slide off with the index card. And that is because of this concept of Newton's first law or the law of inertia, where objects want to stay in the state they're in, either moving or not moving, um, unless they're acted on by a force. And inertia is the property of an object that resists changes in motion. All of these here are examples of inertia. So we have the dishes with the tablecloth. Um, and we can see in each of these examples, the objects want to keep doing what they're doing. The table settings are just sitting on the table. They resist moving with the tablecloth when it's pulled because they're not attached to it. So the force isn't actually acting on those objects. And the coin doesn't slide off with the card when it's flicked, when the card is flipped off the cup. It resists that motion and then just falls down instead. And then you can also slam a hammer down, and that tightens the hammer head because the hammerhead doesn't stop immediately when you slam the hammer down, so it ends up tightening on top. And all of these objects show the default for an object in motion or at rest is to keep doing what it's doing. Okay, so Newton's first law, or the law of inertia, says that objects will keep doing what they're doing unless a force acts on them. But wait a second, what's a force? We haven't talked about that yet. We already have that part. So a force is a push or a pull. It can require direct contact, like touching an object, or work at a distance, and its units are newtons, which are given by a capital N. So it can be you literally pushing or pulling on an object, like pulling the tablecloth out from under those dishes, or it can be something that acts at a distance without something needing to touch it. Like you can drop something and the force of gravity pulls that down without like I don't know, the Earth's hand coming and pulling the object down. Direction matters in forces just like it does in velocity and acceleration. So a force to the right is going to be positive, and it doesn't mean that when you're presented with these forces that they're going to be displayed as positive and negative. And you'll see that in a couple minutes on a different slide. But when you are figuring out what the forces combined add up to, you treat the ones that point to the right as positive and the ones that point to the left as negative. And you only can sum up the regular way anyway. There's other strategies for mixing it, but you can only sum up forces that are in the horizontal direction with each other. And same with vertical. So you can only combine forces that are vertical with each other, and you can only combine forces that are horizontal with each other. So when the force is pointing up, it's positive, and when it's down, it's negative, just like with other kinds of motion. And we'll get into this a little more in a minute. So a concept we're going to be working with is net force. It just really means the sum of the forces or the total forces acting on an object. And when you're summing the forces, you have to take into account both the direction, like if they're vertical or horizontal, and if they're going to the left or the right. So we have this table here, and in the column on the left, we see the forces applied to this object, and on the right, we have the net force, or the sum of the forces. So this first one, we have two 5-Newton forces to the right. So those are both going to be positive, and they just combine with each other. So we end up, our net force is just 10 newtons to the right. The second one, we have 5 newtons to the right, so that's positive, and we have 5 newtons to the left, so that's negative. So when we sum those up, when we combine them, we end up with 0. So the net force on this one is 0. And then we have, for this last one, positive 10 newtons to the right and negative 5 newtons to the left. So when we combine those, we're subtracting 5 from 10, and we get 5 newtons to the right as the result. And just a reminder, these forces are vectors, again, just like velocity and acceleration too. So that means that the size, like how big they are, or that like numeric value of like 5 newtons, 10 newtons, those matter. And then also the direction, if it is to the right or left or up or down, all of that has to be taken into account because these are vectors, and we care about both how big they are and what direction they're pointing in. There's also a concept of equilibrium, and this means that the net force or total force on the object is 0. So that's what like this third example from the table, or sorry, the second example from the table was, where we had 5 newtons to the right and 5 newtons to the left, and that gave us a total net force of 0 newtons. So that would mean this block is in equilibrium. And this is a way to write this in an equation form. So this is sigma, and it means sum, and then F for force. So it's saying the sum of the forces, or the net force, equals 0. A book sitting on a table is in equilibrium. We know that the force of gravity is pulling down on it, but if it is in equilibrium, like I said, there must be another force pushing up on it. Otherwise, that net force wouldn't be 0. And if it's on just any kind of surface, honestly, that force is called the normal force. And normal means perpendicular, as in like we have a horizontal surface, and so our force is vertical, 90 degrees from it, meaning perpendicular. But it's also called the support force. So on this book, we have the force of gravity pointing down, and we have the support force pointing up. And since I said that this book is in equilibrium, these forces should be the same size, but pointing in opposite directions, so that the net force, or the total force on the object, the book in this case, is 0. There is also a concept of dynamic equilibrium, and this just means that an object can be in equilibrium and still be moving. And equilibrium means that the net force, or the total forces acting on the object, is 0, but that doesn't mean that it's not moving. Like there's no rule against that. So as I said, Newton's first law said an object in motion will stay in motion unless a non-zero force acts on it. That means a non-zero net force, total force. And if motion is changing, that's how we know an object is or is not in equilibrium. If the motion is changing, then the object is not in equilibrium. But if the motion is constant, So if it is either not moving at all or moving in simple motion, then it is in equilibrium. Okay. We're gonna take a look at this example here. We have a painter on a scaffold and the system is in equilibrium, but we're only seeing 3 of the 4 forces acting. And we want to figure out what the weight of the scaffold itself is that gives us equilibrium of the forces. Okay, so here's our painter on his scaffold. And we have these 2 forces up. So up is positive. Up is positive. So let's sum our forces. Remember, this sigma just means sum of the forces. So we have 400 newtons up and another 400 newtons up. Those are both positive. And then we have 500 newtons down. So we end up with 800 newtons minus 500 newtons, and that gives us 300 newtons. But this is supposed to be in equilibrium, right? So that means that this 300 newtons down is our missing force. And we can double check that by saying, okay, let's say, maybe I'll change color. Let's say we think this is 300 newtons down, and we can just confirm, okay, that would be negative 800 newtons and positive 800 newtons, and that's going to give us 0 total. So the scaffold, the missing force is 300 newtons, and that would make the forces cancel out and put our scaffold in equilibrium. Okay, now Newton's second law. So this also builds on the idea of equilibrium. So if the net force is not 0, then the object is accelerating in some way. So what Newton's second law says is that a net force on an object causes it to accelerate. And that makes sense because I said a minute ago that if there's a net force, that means there's changes in the motion. And if there's changes in motion, there's acceleration. So it makes sense that if there's a net force, there must be acceleration because the motion is changing. So we have an example here of a force of a hand accelerating a brick. So this hand is applying a force to the brick, pushing it so that there's a net force, and that's causing acceleration, changing the motion from like at rest to moving. If both hands are pushing and able to apply twice as much force, that also means it's going to go twice as fast. And one thing to note, if you look at an object and it isn't accelerating, but the forces you know about don't cancel all the way out, then that just means you're likely missing a force that is acting. Just like we were with the scaffold, like we knew there was not a net force, we knew there was not acceleration, so we had to figure out what force we weren't seeing. Oops. There we go. So mass and weight are 2 different things. I know in like regular language we use them. Well, we actually usually use weight to mean mass in regular language. But when we're dealing with physics, we have to be careful about the distinction. So mass is the amount of stuff that makes up an object. So it's similar, it's kind of a measure of the inertia or how hard it is to change the motion of an object. So if something has more mass, it's going to be harder to change its motion. Whereas weight is just actually a force. It is the force due to gravity. And it does depend on the mass of the object, but it also depends on the local acceleration due to gravity. So, for example, the moon doesn't have as strong of a gravitational force as the Earth does. So if you were on the moon, your mass would stay the same, but your weight would be different because the local acceleration due to gravity is different. And mass is what resists acceleration or resists changes in motion. So mass is a measure of how hard it is to change the motion of an object. And acceleration is that change in motion. And we can put those ideas together and say that mass is a measure of how much an object resists acceleration. Because again, acceleration is change in motion. So back to Newton's second law, forces cause acceleration, mass resists acceleration. So that tells me that force, mass, and acceleration are all connected. And this is how they're connected. Acceleration is equal to the net force. Remember, the sum of forces or total force on the object divided by its mass. So that means an object's going to travel faster or have a faster, bigger acceleration if there's more net force on it or if it has less mass. Because remember, we have mass on the bottom of a fraction, and the smaller the denominator or bottom of our fraction is, the bigger the overall result. And remember, again, you can always test that. You don't have to always have a feel for it. It can make sense to just type in like 1 divided by 2 and 1 divided by 20 and see how different those are. And as we said, forces and acceleration are vectors. Mass is not a vector. Mass is just a feature of an object. So we have two vectors here, two variables that depend on size and direction. So they actually need to be in the same direction. So the acceleration is going to be in the same direction as the net force. And we can look at this example here to think about what is the direction of the acceleration for this block. So we have two 5-Newton forces to the right. That means they add up to get our net force of 10 newtons to the right. And acceleration needs to be in the same direction as the net force. So the acceleration is also to the right. We would need to know the mass of this block to be able to figure out the acceleration itself. But we can figure out the direction. So let's think about this one. Maybe pause the video and figure it out for yourself for a second. Or we'll just talk about it. So we have 5 newtons to the left. That's going to be negative. And then 10 newtons to the right, positive. So 10 minus 5 is going to be 5 newtons to the right. So our acceleration and force are both to the right. Our net force, excuse me. Let's talk a little bit about units and variables. So force is given in kilograms, which that's mass, times meters divided by seconds squared, which is acceleration. And this can help us figure out, right, the equation for force. If we're just looking at these units, we have mass times acceleration. Force equals mass times acceleration. And that makes sense because the previous equation we were looking at was acceleration equals force divided by mass. And if we wanted to get acceleration by itself in this relationship, we would just divide mass on both sides, and that would give us that other form of the equation. But that's a really nice way, especially if you forget the relationship between variables, but you like either know the units or you can look at the units. You can see how the equation like works out. The relationship between these variables works out. And let's talk a little bit about forces and interactions now. So in order for me to exert a force on an object, it needs to exert a force back on me. If I push my hand into the wall, there is a support force, or that normal force, pushing back on my hand. Same thing if you press your hand on the table, you apply a force to the table, and the table applies a force back. An interaction requires a pair of forces acting on different objects. So we have my hand on the table and the table on my hand, or my hand on the wall and the wall on my hand, or the examples on the slide. We have a boxer hitting a punching bag, and we see that the impact force on the bag moves, the bag moves and deforms, and we see the force on the boxer from the bag because it brings his fist to a stop. So if there wasn't that interaction there of forces on both sides, the boxer's fist wouldn't stop, or also the bag wouldn't deform or move. And then we have this hammer hitting a nail, or stake, I guess. And the force from the hammer pushes the stake into the ground, but the force from the stake brings the hammer to a rest. So these examples show how these interactions, on one side, we have an object like, I don't know, like distorting the punching bag or pushing the stake into the ground. And on the other side, the response force brings those two objects, the fist and the hammer, to a stop. This brings us to Newton's third law of motion, which says whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Or another way to say this is every action has an equal and opposite reaction. These forces are called action-reaction pairs or third law pairs, but it doesn't actually matter which one is the action and which one is the reaction. These things are happening simultaneously, and it's not even always obvious. Like in the case of the boxer and the punching bag, we know that the boxer is kind of like the one active in the situation. Like the punching bag would just be hanging there if there was no boxer to punch it. And the stake would just be sitting there if there wasn't a hammer to hit it. So those do feel like we have like an action or an actor and a reactor. But not all situations work that way. And in general, those forces are happening at the same time. So don't worry about which one is an action and which one's a reaction. Just what you want to worry about is which forces go together. So here's some examples. We have a car driving. So the tire pushes on the road and the road pushes back on the tire, and that's what pushes the car forward. We have a rocket pushing out gas, and that ends up with the gas pushing the rocket forward, launching the rocket. We have a man pulling on the spring, and the spring pulls back on the man. And then we have someone dropping a ball off the Tower of Pisa. And the earth pulls on the ball, and the ball pulls back on the earth. And that one might sound a little weird, but we will touch on that concept in a moment. Let's look back at Newton's second law again. So acceleration is equal to the net force divided by the mass. So if we think about a falling object, like I said, the earth is applying a force on the object and the object is applying a force on the earth. These forces have the same magnitude or size, but we really only see an effect on the falling object, not on the earth. And that's because of the mass here. Because the earth is way more massive than any object we're dropping. And so if we have a really big number at the bottom of our fraction, that's going to give us a really small result. So the big mass of the earth means that the acceleration or any real reaction or effect we notice on the earth is imperceptible, teeny tiny. But because the ball has a much smaller mass, then we do see the acceleration as a result of that interaction. So the acceleration is the effect we see from a force acting on an object. So for the boxer, the punching bag applies a force that brings his fist to a stop. It was moving, now it isn't. Then that's a change in motion, right? So there must have been acceleration to bring his fist to a stop. So the acceleration or effect is different even though the force is the same. Let's look at this example. I want you to take a moment and think about it. But first, a big truck hits a small car. Is the force the same on each of these? Is the effect the same? So pause if you need a moment to just kind of think about this and be honest with yourself. I bet your first thought is that there's no way the force is the same, because obviously the car is going to be in worse shape than the truck after this. But that would be a different effect on the car versus the truck. That doesn't mean that the force they experience is different. So remember, Newton's second law says that acceleration is equal to the force divided by the mass. If we assume, as Newton's third law says, that the forces are the same, we know these masses are different. The truck is bigger and heavier than the car, so it's going to have more mass. And the same force divided by a smaller mass would give a bigger acceleration than divided by a bigger mass. So it isn't the force that results in the different effects, but the mass that produces different accelerations or effects on each object. So I just want you to spend some time thinking about this idea, because I know intuitively you're still going to kind of feel like, well, the car feels more, so it must be more force. But allow yourself to kind of change that view. Say, okay, the force is this, let's say the force is the same, even if you don't fully buy it. And think about the differences in the mass and therefore the differences in the acceleration. And then to wrap us up, I just want to look at some units since we introduced a new idea. So we've talked about position as in X for horizontal and Y for vertical, and that's a measure of distance from some origin, and we usually give that in meters. Time, that's given with a little t, and that's going to be in seconds most of the time. Then velocity, you can label that with a v. That's a distance divided by the time, or the distance traveled over a time period. And that's given in meters divided by seconds, or as they say, meters per second. Acceleration, that's given by an a, and it's the change in velocity divided by time. And also, just a note with acceleration, remember, if the motion changes, there must be acceleration. And then because velocity has units of meters divided by seconds, and then time is in seconds, we end up with the units of acceleration as meters divided by seconds, or as we say, meters per second squared. Mass, we talked about before, but now we really have a definition that it's the stuff that makes up an object, and its units are kilograms usually. And then force is a push or pull applied to an object. Units are kilograms times meters per second squared, which is mass times acceleration. And this is also has its own unique label of newtons given with a capital N. Okay, that's all for today.